Hello guys, welcome back to the Introduction to Number Theory. Now we will discuss Euclidean algorithm and the linear representation of the greatest common divisor. First of all, let's start from the Euclidean algorithm. As any algorithm, it consists of steps. So the first step is dividing A into B with remainder. And we know that remainder should be less or equal to 0 by norm and less than the norm of B. So the second step is also a division with remainder. We take B and we divide it into the obtained remainder with some other remainder, where this other remainder should also have its norm less than the norm of the previous remainder. So let's pay attention to the moving of these variables. So B goes here and R1 goes here. What comes next? The third step of the Euclidean algorithm is to take the first remainder and divide it into the second remainder, obtaining the third remainder. Standard conditions should hold. And pay attention to the life of variables. So we see that R1 goes here and R2, the second remainder, goes here, and we get the third remainder. Such steps should be continued as long as it is possible. So we have and so on and so on. And what happens in the end? We can notice that the norm of remainders is getting less and less. So the first remainder is less than B, and the second remainder is less than the first remainder, and the third remainder is less than the second remainder, and so on. But we know that the norm of the remainder is a non-negative integer, so sooner or later, its norm will become 0. And let's find this step where the norm becomes 0. So let's call it the kth remainder. We divide it into k minus 1, the remainder with number k minus 1, multiplied by q with some number, it doesn't matter, plus the remainder with number k plus 1. And this final remainder, is equal to 0. So this is the final step of Euclidean algorithm, and we can no longer divide with remainders because we got a remainder equal to 0. Okay? So this is where Euclidean algorithm is finished. And why did we do all these divisions? The answer is simple. Let's notice that if we take the greatest common divisor of A and B, A is over here and B is over here, then it is equal to the greatest common divisor of B and R1, our first remainder. So I'll try to explain. Actually, it's very simple. So here we have B, it's the same element as here, and the first remainder. So if A and B have some common divisor, then A and B are divisible by some element, then obviously R1 is also divisible by the same element. And the other way, if R1 and B are divisible by some element, then A is obviously divisible by the same element. So actually, pair AB and pair BR1 have the same common divisors. Therefore, the greatest common divisor of A and B is obviously equal to the greatest common divisor of B and R1. Since all steps of the Euclidean algorithm are almost the same, we can conduct that this common divisor is equal to the common divisor of R1 and R2, which is equal to the common divisor, the greatest common divisor of R2 and R3, and so on and so on. And finally, we get the greatest common divisor of the final two remainders, which are Rk and Rk plus 1. So Rk and Rk plus 1, which is, since Rk plus 1 is equal to 0, which is just simply equal to Rk. So finally we get that Rk, our last non-zero remainder, is actually the greatest common divisor of A and B. This way, Euclidean algorithm helps us calculate, if you like, the greatest common divisor of two elements A and B. But it also helps us gain the linear representation of this greatest common divisor. First, let me remind you of what linear representation is. So, if we take the greatest common divisor of A and B, it can be represented as a linear form ax plus by, where x and y are some elements of the same ring where A and B belong. It is a Euclidean ring. We have talked about Euclidean rings in the previous parts. Okay, so why is it so? Why do these x and y exist? Let's take a look at the Euclidean algorithm. First of all, notice that R1, our first remainder, can be represented this way. It may mean linearly using A and B. So we have R1 is equal to A minus B1 multiplied by Q1. Okay, let's take the second remainder. What can we say about the second one? We can say that this is equal to B minus R1 multiplied by Q2, which is equal to, we simply use the previous equation gained here, A minus B1 Q1. Actually, I don't have to read this. You can see it by yourself. But take a look at this expression. It is obvious, I think, that it is also a linear representation using A and B. So we have that R2, here R2, can be represented linearly using A and B. Here is A, and here is B, and here is also B. So we can say that it is A multiplied by something, and B also multiplied by something. Okay, so finally, when we get this way, if we continue downwards the Euclidean algorithm, finally we'll get that the last remainder will also be represented linearly using A and B. So we can say that Rk is equal to A multiplied by something, which we denote x, plus B multiplied also by something, well, where by something I mean an element of the ring. And this way, we get that the last remainder also has a linear representation in A and B, but let's just remember that the last remainder is none less than greatest common divisor. So we can say that instead of the last remainder, here we have greatest common divisor of A and B, and thus our statement is proved.